There's currently a very extensive range of spark plugs available to vehicle manufacturers, and they're all designed to deliver sufficient current to ignite the air-fuel mixture within the combustion chamber. In a conventional ignition system, current flows from the ignition coil and lead to the spark plug terminal. The exception to this would be when a wasted spark system is used. The spark plug is quite simple in construction and has changed little since first invented in 1860. It has been improved over the years by Bosch, Champion and Denso, but its principal construction and operation remain the same. The spark plug is connected to an ignition source capable of supplying high voltage current flow in the system. Current will flow from this source to the spark plug terminal and then through a resistor to the centre electrode. The current will always travel the path of least resistance to ground, in this case to the side electrode. Initially, the air-fuel mixture within the combustion chamber acts as an insulator to current flow, but as the voltage rises, these insulating features or dielectric strength is overcome. The air-fuel mixture in the vicinity of the centre and ground electrode will now conduct current and electrons will flow across the gap. Now that we understand the basic operation of a spark plug, let's look at the different components used in their construction. The metal shell is designed with the thread that screws into and seals the combustion chamber. The seal may take the form of a compressible washer or a tapered seat. The shell holds all the spark plug internal components in a neat package and acts as the earth point to the engine. Within this shell is the insulated central electrode, which protrudes through the insulator into the combustion chamber. The electrode is connected to the terminal at the top of the plug. The shell may have one or more ground electrodes built into the side. These allow the current to travel to earth and complete the ignition secondary circuit. Most spark plugs used for road-registered passenger vehicles will also have an inbuilt resistor, used to assist in eliminating electrical or radio interference to other components in the vehicle's electrical system. Most modern-day spark plugs have steps or ribs on the external wall of the insulator. These steps are designed to lengthen the distance between the upper insulated terminal and the earth shell as much as possible. This design removes the potential for current to track down the outside of the spark plug through dirt or moisture. Spark plugs are designed to fit into cylinder heads or combustion chambers of various sizes and designs. It's for this reason we find spark plugs with a different reach or shell thread length. A spark plug designed to go into a long reach head should never be used in a short reach situation. A plug that protrudes too far through the cylinder head runs a high risk of being hit by a piston, causing damage. A short reach spark plug installed into a long reach situation will result in an inefficient burn, as the cylinder head will shield the spark as the plug fires. Spark plug threads can become encased in burnt fuel and oil deposits, which may damage the cylinder head when removed. The heat range of a spark plug is determined by the length of the insulator and to some extent by the material used in its construction. A hot plug has the ability to retain heat at the plug tip due to the simple fact a longer period of time is needed for heat to dissipate through the insulator to the cylinder head and cooling system. A cold plug has a very short heat path, so any retained heat will be dissipated much faster. Typically, the heat range of spark plugs will vary based on engine design. The heat range will determine the thermal characteristics of the spark plug. Generally, lower compression engines don't produce a large amount of combustion heat. Hence, they use a hot spark plug. This means the spark plug will heat up easily and reach its optimal operating temperature faster. High-performance engines, on the other hand, produce a large amount of heat, so a cold spark plug needs to be used to resist the heat produced within the combustion chamber. If the spark plug selected for the engine is too cold, carbon deposits will build up between the centre electrode and the shell. These deposits cause a ground path for the high voltage current to follow. This results in engine misfire. If the spark plug heat range is too high, abnormal pre-ignition may be induced. This will lead to melting of the spark plug electrodes as well as piston damage. Using a spark plug with the correct heat range for the engine design will result in self-cleaning and optimal ignition operation. Centre electrodes used in standard spark plugs are made of a nickel alloy with a high copper content, which enables the plug to heat up quickly and also dissipate heat quickly, resulting in a very wide heat range. Today, the use of platinum and iridium in spark plugs is very common. Nickel-copper alloy is a great conductor, but is subject to corrosive degradation. Platinum, on the other hand, has excellent corrosion-resistant properties, but does not conduct electricity as well as the nickel alloy type. Iridium is a good conductor and can be up to 6 times harder than platinum. As a result, an iridium electrode can be formed utilising a small fine tip, contributing to a greater spark concentration. The material used in electrode construction has a direct impact on the service life of the spark plug. The design and shape of the ground or centre electrode plays a very significant part in the plug's ongoing performance. The ability of these metals to perform under duress can be best observed in the size of the electrodes. A typical nickel-copper alloy electrode has an average diameter of 2.5 millimetres, with a service life of around 20,000 kilometres. An iridium centre electrode only needs to be about 0.5 millimetre in diameter, with a service life of around 60,000 kilometres. A platinum centre electrode has an average diameter of 1.1 millimetres, with a service life of around 100,000 kilometres. Most ground electrodes are welded to the spark plug shell. These electrodes can be manufactured from the same material as the shell or may be plated with platinum or iridium. Some spark plug manufacturers machine a groove into the ground electrode. The principle of this groove is technically simple and also very effective. It forces the spark to occur at the outer edge of the centre electrode, where it is easier to ignite the air-fuel mixture. In addition, the voltage required to produce spark is reduced. These two features give the benefit of improved ignition of the air-fuel mixture. A single-side ground electrode is still the most commonly used, but multiple electrodes are increasing in passenger vehicles. Using a spark plug with extra ground electrodes does not mean there's more spark. There's just other options for the current to jump the gap. The current will always take the path of least resistance. So under extreme operating conditions, a spark plug with 4 ground electrodes has more chance of igniting the air-fuel mixture than a single electrode. Spark plugs must be designed to have an air gap between the centre and ground electrodes. This is the ignition point for the air-fuel mixture within the combustion chamber. The air gap is different for every vehicle. Always check the manufacturer's specifications for this information. If this was too narrow, it will often result in a weak and inefficient spark. A narrow gap requires a lower coil firing voltage, resulting in a poor fuel burn, rough engine idle, and a possible misfire. A gap that is too wide will often result in poor engine efficiency and rough running. A much higher firing voltage will be needed. If there is insufficient voltage to jump this gap, the spark will be weak and the engine will misfire. Controlling the spark and thus the burn, is paramount to ensure fuel efficiency, emission outputs, and demand for power. Incorrectly gapped spark plugs will affect all of these functions. Manufacturers determine the best electrode gap for the engine design. This ensures a correct burn of the air-fuel mixture in the combustion chamber. All spark plugs are identified by a part number designated by the plug manufacturer. Decoding these part numbers can become easy with some practice. NGK is probably the easiest to decipher, as it uses a very simple numbering method. When looking at a spark plug using a part number of BPR 5ES11, we can observe that B indicates the thread size. In this case, it's 14mm in diameter with a shell hex size of 13/16. P denotes the insulator is of the projected design. R means this type of spark plug has an inbuilt resistor. 5 is the heat range. NGK uses a low number to denote a hot plug, while a high number is used for a cold plug. 5 is right in the middle. E stands for the shell thread reach. In this case, it is an extended reach of 19mm. S tells us that the centre electrode is a standard type, constructed from nickel-copper alloy. 1,1 is the air gap that the plug needs to be set to before installing in a vehicle. This is read as 1.1mm. Modern engines and electronic systems rely on technicians making the right choice when selecting and installing spark plugs. Understanding these basic principles will make that choice a little bit easier. Thanks for watching.